If you want to look at it now, though, before the office one comes in, you decide whether you want to order it or not. You can look at mine.
Has
Okay.
everyone turned in their form? And does anybody need a form but forgot to turn it in? It's due today.
Off. Yeah, that'd be better, thanks. This thing's not on, it's not on. Is it on my, has to turn on my, really? Oh, it's going to that.
Yeah,
And not
it's
this
just the
one.
widescreen, yeah.
All right. Are we all here? We are, all right. I know many of you don't know me. My name is Mike Doré. I'm actually an igneous petrologist. I dabble in metamorphic petrology a little bit here and there. And I actually teach a 500 level course on metamorphic petrology if you'd like to know more. How's that for like kind of a more missionary intro to metamorphic petrology? The Alps have some absolutely spectacular metamorphic rocks, which I hope to convince you here of a minute. I also have similar blue schist rocks and eclogite facies rocks. These are from the island of Syros in Greece, but you can look at those to see some of the similar type of rocks you'll see. If you do happen to see some really cool metamorphic rocks, would you do me a favor? Collect some. For instance, this. How do you like that? This is an eclogite. This is kyanite. This is a pyroxene called omphacite, I'll let you introduce in a second, and garnet. That looks like a cut slab, but if you see anything like that, it'd be pretty awesome. All right, well, before we can start on telling you what the metamorphic rocks are like, I want to give you a brief overview of some of the things I think you need to know about metamorphic petrology before you go, so you'll have some sort of appreciation. Petrology, the terms we use, is like a foreign language, so you got to plug certain terms in your mind in order to understand the conversation. So I'm going to go over some of those terms, etc., to help you out. First and foremost, you need to recognize or understand metamorphic facies and the general fields where they lie on this pressure temperature diagram. Most of you, I think, have had petrology. Anybody not? Okay. I don't know if they discuss any of this in 101 or 111. There may be just a little bit here and there. But just to review, here we have pressure in kilobars versus temperature. And each field represents the PT space of a specific metamorphic facies. We have zeolite facies, prehnite papilite facies. Some of those you've probably never heard of. We could just call this, for our purposes, sub-green schist facies. We come to green schist facies and fieldlite facies and granulite facies. Those are the ones you probably are most familiar with, because most continental collision type origins are within this medium pressure regime. We also have blue schist facies and eclogite facies, and the Alps have spectacular areas of blue schist and eclogite. So what I want you to do is introduce you to the minerals that characterize blue schist and eclogite. So when I use those terms, you'll have a sense for what they mean, their compositions. And also when you're out in the field, you go, wow, that is the most beautiful omphacite I've ever seen in my life. Okay? So, blue schist facies. Blue schist facies is characterized by a sodium amphibole called glaucophane. There's this formula if you care. A calcium aluminosilicate called lawsonite. And if it has a mica, the mica is similar to muscovite, but it's termed phengite because it has higher silica and magnesium concentrations than most pure muscovites. But for your purposes, you could consider a muscovite, though I'll show you optically it looks a little bit different. Okay? Eclogite, on the other hand, is characterized by omphacite. This is a pyroxene. Think of an augite, a calcium, iron, magnesium augite, but it has some sodium in it. Remember, there's a sodium end member of pyroxenes called jadeite, which is a sodium aluminum pyroxene. So this have a little bit of the jadeite component in it. It's not jadeite per se, but it's other things in it that we then use the term omphacite. And it's also characterized by garnet. You'll recall that there are several end members of garnet, right? You all remember your mineralogy is just like that. It's ingrained, never to be forgotten. The almandine end member is the iron end member of garnet. Pyrope is magnesium, simply substitution. Spessartine is manganese, and grauchular is calcium. So the eclogites will have garnets that have various proportions of those end members. Okay, so we'll see these throughout the afternoon here. I'll show you pictures of them in the field, and pictures in thin section as well. So what do we mean by metamorphic facies? Looked at Belucius facies, for instance. Escola was one of the masters of metamorphic petrology, goes way back to the early 1900s, who wrote, "A metamorphic facies includes rocks which may be supposed to have been metamorphosed under identical conditions. As belonging to a certain facies, we regard rocks which, if having identical chemical composition, are composed of the same minerals." I.e., if you take, say, a Moore basalt, you metamorphose it to this condition, anywhere in the world, then that Moore basalt will have the same minerals. Or if Belucius facies, that Moore basalt will have those same minerals under different facies. Another famous petrologist of mid-century, 1900s, was Turner. A metamorphic facies is a set of metamorphic mineral assemblages repeatedly associated in space and time, such that there is a constant and therefore predictable relation between mineral composition and bulk rock chemical composition. Whether that rock be a metasediment, and I'll use the word peelite. I don't know if you guys have used that word before. When metamorphic petrologists use the word peelite or politic rock, they mean basically a schist, a rock that was originally clay rich. I don't think sedimentary petrologists use the word peelite, but metamorphic petrologists do. So, metamorphic facies, yes?
Well, so what does metasedimentary mean?
Metasedimentary means it's simply a metamorphosed sediment. The origin, the protolith of the rock was a sediment, sedimentary rock. Okay? So the metamorphic facies were first defined using mafic rocks. So again, with zeolite, prehnite, pompelliite facies, you don't care about those minerals right now because you're not going to see them. But Belucius facies is characterized by glaucophane, again the sodium amphibole, lawsonite, calcium aluminosilicate, eclogite, it's characterized by garnet, and ophidic pyroxene. But of course there's green schist and amphibolite and granulite facies as well. Europeans don't use the term epidote amphibolite facies, they just lump them together as amphibolite. It's Americans who do that, and frankly we're kind of dumb to do so, in the sense that if you're looking at a rock in the field, can you tell whether the plagioclase is alluvioclase or andesine? If you can, you're better than I am. And what happens is that the epidote amphibolite facies, of course, has epidote and more sodic plage. At higher grade, the epidote breaks down, it gets incorporated in the plagioclase, gets more calcium. So only Americans will use this subdivision. You can just lump them in as amphibolite facies for most purposes. Well, way back in the 1890s, there was a very famous geologist named Barrow, and he was wandering around Scotland. I gotta admit, I admire these masters of petrology who, simply out of curiosity, went out in the field and observed things. Well, Barrow observed that as he's walking somewhere up here in Scotland, he says, oh, as I go this way, all of a sudden I see porphyroblasts. Porphyroblasts is the metamorphic term for, say, a phenocryst. He wanders up this way, and he says, oh, I see porphyroblastic chloride. He goes a little further, and all of a sudden, boom, biotite appears. And then garnet appears, and starlight, kyanite, sillimanite, etc. Then this guy goes, wow, maybe I can map these out. So he goes across several places and maps out where the first appearance of chloride is, of garnet, etc. These became known as index minerals. They're indicative of increasing metamorphic grade in this direction. So you can see with the politic rocks, for instance, if you've got starlight kyanite, then you're in the amphibolite facies. Sillimanite, you're up in the granulite facies, etc. And of course, you can do this with carbonates, with ultramafic rocks. They all have their own set of unique minerals at whatever facies they've been metamorphosed to. It's been observed since then that there are distinct, shall we say, pressure temperature regimes for metamorphic rocks depending on the tectonic setting. So for instance, areas of high heat flow, for instance at contact aureoles, will give us a low pressure metamorphic band like that. Most continent collision belts have medium pressure metamorphic minerals that occur across this band, and subduction zones are characterized by high pressure metamorphism. Let me point out one other thing on this diagram. This is the aluminosilicate triple point. And again, you remember aluminosilicates, Al2SiO5. There are 3 polymorphs. The high pressure aluminosilicate is kyanite, the low pressure is andalusite, the high temperature is sillimanite. And there are their respective fields. This is another thing to plant in your brain. never forget it. Name your children kyanite, silmonite, and andalusite, because that's what metamorphic petrologists do. Okay? So contact metamorphism is low pressure, orogenic belts medium pressure, and subduction zones will metamorphose rocks to high pressure. Now let's look just for a second at medium pressure metamorphism, or that of orogenic belts. Start with this figure. This shows a hypothetical cross section through the crust, and these are isotherms increasing temperature with depth. What happens when an orogenic collision occurs? Well, you have rocks that are thrust up over other rocks. And in terms of the rocks themselves seeing this, it's practically instantaneous. Now, yeah, it'll take millions of years, several sometimes, but these guys get loaded very, very quickly as far as they're concerned. So let's suppose that we want to consider a rock maybe sitting right here. Okay, this is the upper plate. It was over here. It gets pushed up over the lower plate. Originally, in this setting, we had a steady state geotherm with increasing temperatures with depth. But all of a sudden now we have the rock from over here pushed up over, and the base of that, say, is about 500 degrees or so. Okay? So what we're seeing then is the upper plate has this geotherm starting at whatever degrees, going down to 500 at about 10 kilobars. But this rock that just has the upper plate sitting immediately above it will be still pretty cold, say 100 degrees or less. So that's here. So all of a sudden we go into the upper plate, getting hotter, and then bam, we drop back down in temperature right there, and then we go back in higher temperature with increasing depth. So we have this sawtooth perturbed geotherm.
And so why they have different temperatures?
This is just the normal geothermal gradient going down into the crust. Okay, so up here at the surface it's pretty cold, but the deeper and deeper you go down into the lower crust, you get pretty hot.
Yeah, but why it's not like, why it goes like 500 and then jumps again to 100, 200?
Think of my top finger being 100, my bottom pinky being 500.
Yeah.
You take that and you stack it on top of each other.
Okay.
Then we got 500 next to 100.
Okay.
So we have a big temperature jump across that boundary.
And it remains there like for a while, or?
That's
Yes.
immediately.
Yes, and that's the essential point. Okay, so let's suppose we're going to consider a rock sitting right here. That's about 200 something degrees. What does that rock see as the upper plate is thrust up over it? The first thing it sees is a big increase in pressure. It takes a long time for that rock to heat up. Rocks are poor conductors of heat. So that rock will first see a big jump in pressure. These represent millions of years. So eventually, this sawtooth pattern will be relaxed, and it'll sooner or later reach that state of a steady state geotherm, but it's going to take a long time. So after 20 million years, it's still not there yet. It hasn't reached its maximum temperature. 40 million years, about 60 million years, according to several people's models, will take for this rock that was originally at 200 something degrees to finally heat up completely to where we have a steady state geotherm again. Now note that after 40 million years, you've had a lot of erosion. So what was way up on here on the top is being eroded away, and then this rock that was originally sitting right here is being exhumed. So the pressure is decreasing as it's still heating up. And again, it's not till 50, 60 million years later that this metamorphic rock reaches its peak temperature. Long after it's reached its peak pressure. Notice its peak pressure is way up here, but it's still being metamorphosed because it's heating up, and there are all sorts of metamorphic reactions as you proceed this way, to finally reach a peak temperature here, which is much lower pressure than the original pressure when this thing was first loaded. Now let's consider another rock. Let's suppose that this path here, and note that it's a clockwise pressure temperature path. Okay, this is characteristic of orogenic belts, where thrusting takes place and loading takes place.
So each of those dots represents the same rock, or?
Yes, the same rock. This is the path.
Why is its depth?
Why is its depth
decreasing?
decreasing? Because as you've stacked the rocks up and you've thickened the crust, then erosion kicks in. And the top of the mountain
Oh,
range starts to
okay,
get
right.
eroded and eroded and eroded. So the pressure on that one rock gets decreased and decreased. But again, it's still heating up over that whole process. So let's suppose this path right here is the one we just talked about. What if you consider a rock that is at, say, 500 degrees deeper in the crust, somewhere down in here? Well, that sees the same jump in pressure, even though it started at a deeper pressure. It gets loaded as well. It starts to get heated as well. It takes 60 million years to reach its maximum temperature. But note that each of these two rocks undergo a completely different PT path under different pressure temperature conditions. This rock that has its metamorphic assemblage fixed here at, say, maximum pressure or temperature doesn't see what this rock saw at all. So you could consider a series of rocks at different pressures, A, B, and C. They each go through their own pressure temperature path. They each reach their maximum temperature millions of years later. And because it's crossing metamorphic reactions as it's proceeding up temperature, and many of these metamorphic reactions are dehydration reactions, say mineral A, that's a hydrous mineral, breaking down to a product B, liberating water. Okay? It goes through a series of those to reach this point. Well, if that water escapes, then the assemblage that formed at maximum temperature gets locked in the rock. That's what gets preserved. And as it comes down the retrograde path, or the cooling path, it'll preserve that mineral assemblage unless water can get into the system again, and then you'll backtrack across those reactions as you go down temperature. But what you see in the field, this is what Burroughs saw. Let's say path 1 is the PT path that produced chloride. Path 2 would be biotite. Path 3 would be garnet, sylmanite, etc. What he saw in the field, and what you see in the field, are the peak temperature assemblages that are locked in. Even though the path of the rock went crazy like that, it forms an array, or a metamorphic field gradient, it's called, that cuts through a path like that. Now, there are several interesting implications of this. First, a PT path followed by any individual rock is not parallel to the metamorphic field gradient. Okay? So, for instance, this rock goes up as it's loaded, it starts to heat, comes down, the final assemblage gets locked in at maximum temperature, then it goes a retrograde path. Okay? Notice that's very different than what you see in the field. You're just going from rock A to B to C to D, etc. Okay? So what you see in the field is not how the rocks actually got there. They probably got dropped down from higher pressures as the thing heated over time. That means it's not possible to infer the reaction history of a high-grade rock, say for instance rock F, by examining the mineral assemblage of a rock of similar composition that's at lower grade, say rock C. Rock C goes under a very different path than the one that formed rock F. That's because the rock at high grade never passed through the peak metamorphic conditions of the low-grade rock. So low-grade rock C goes through some path like this. It's at 6 kilobars and 400 degrees. But rock F started way up here somewhere. Perhaps higher temperature, higher pressure. He goes way the heck up here and comes down. So completely different set of metamorphic conditions than something lower on the metamorphic field gradient. It also means that the maximum pressure, say up here, of any given rock does not equal the pressure when its final assemblage is locked in at maximum temperature. Okay, those are very different. And because you're passing metamorphic reactions from here to here, then the assemblage that may have formed up there is gone. It's very difficult to find metamorphic rocks that have assemblages that can give you maximum pressure, because most of those assemblages are destroyed as it proceeds down this path, getting hotter and hotter and hotter, liberating water, etc., until you reach point G. Therefore, it's not valid to assume maximum pressure is preserved in the peak metamorphic assemblage that we see in the metamorphic field gradient. Now, this has interesting implications now for collisional settings. A rock that preserves its maximum temperature assemblage, say rock F, may have experienced prior higher metamorphism. So, for instance, right now we go out in the field, we pick up rock E. What do we see? It's in the amphibolite facies. I don't know if you can see that back there, it's kind of faint. But notice rock E was once up in the eclogite facies. It dropped down, constantly changing its mineral composition to finally it reaches the maximum temperature, locks in that mineral assemblage indicative of amphibole facies. Then it cools off. So you'll be out in the Alps, you'll pick up an amphibolite, you say, well, gee, maybe it metamorphosed in a path like that. Well, it didn't. It probably metamorphosed in a path like this with a positive clockwise PT loop.
How did they map these paths if there's no evidence of?
Okay, that's a great question. If you're really good, you can find that evidence.
Okay.
So for instance, you may have a garnet with minerals inside the garnet that will preserve a little bit of this higher pressure stuff. And that's a fascinating topic to try to peek out what those higher pressures could be. But people have been able to do some of these paths with certain rocks. If they get hot enough, then they get just homogenized. But sometimes you can do it. So here is the medium pressure metamorphic path in orogenic belts. And what do we see? Well, sub-green schist, amphibolite, granulite. Okay? But again, they're dropping down into those fields. There, by the way, is your aluminosilicate triple point right here. So andalusite, silmonite, and kyanite up here.
That guy in Scotland, when was that when you first discovered
I think it was
that?
1892, somewhere right in that ballpark. I'd have to go look at the original reference. Okay, now, let's look at subduction zone metamorphism. We just saw this one. And again, notice that this is the metamorphic field gradient, but the rocks are probably getting loaded and dropping down into this region right here. So what about subduction zones? This is a pressure temperature diagram, and I put it on here to show a typical PT path for blue schist. This LAW stands for lawsonite. It shows the stability field of lawsonite. So lawsonite is relatively low temperature. Let's see. One of these curves, it's not labeled very well, one of these curves shows the maximum thermal stability of lawsonite. So you proceed past this, lawsonite changes to something else. But here's a PT path going up through the lawsonite field and coming back down as those rocks come tumbling back out of the subduction zone. Okay, notice these are pretty tight paths. If you could let this rock sit in the subduction zone forever, well, yeah, then it would get warmer and warmer and warmer and come way out here somewhere. But as it goes down into the blue schist facies, and if it tumbles out, then it's got to stay within the blue schist facies. It gets this narrow compressed PT path. I put this up here also to show you the stability of lawsonite. That we're talking, anywhere 10, 15 kilobars or so. So we're getting fairly deep. Now the final assemblage of what goes down into the subduction zone depends on how long it stays there. The longer it's there, the more it's going to heat up, right? So here is the blue schist field here. This is the eclogite field there. You can imagine if you have rocks being subducted rather quickly, then they're going deep fast and they don't get to heat up very much. So they can go way down, get very, very deep. Notice we're in GPa now, gigapascals. So we're really, really deep and we're still in the blue schist facies. But if these rocks take a slower rate of subduction, then they'll heat up more than the cold guys will, and you can actually just kiss the corner of blue schist and jump out into the eclogite facies.
Just as a reminder, what's the equivalent of depth to the pressures roughly?
Kilobars, it's about 3.3 kilometers per kilobar, somewhere in that ballpark. Okay. All right. So whether you end up in blue schist or eclogite will depend on really how much time the rock spends at depth. And if you can subduct it slowly, then yeah, you can heat up those rocks a little bit better. All right. Keep those things in mind. And when you go in the field, I hope you plug them in your minds too, because once you get out there, you'll appreciate what you see a whole lot better. Now, I guess Ron talked to you about the tectonics of the Alps last week. And I don't know what he said to you. One of the problems you'll always have when you start to read about the geology of a particular area, especially a mountain range, some Joe working over here names things differently than somebody working over there. So depending on whose literature you read, they may call the same belt of rocks by a different name. So the one we're going to use is the one that's in this book, and Ron may have named some of these tectonic elements with slightly different names. But what do we got? Well, you got your European plate. This consists of basement rocks that were mainly metamorphosed during the Beriscan orogeny, which happened about 300 million years ago. Then you have an arm of an ocean. This book calls it the North Penic Ocean. You have a continental fragment. Did Ron use this term?
Yes.
Okay, I see no's and yeses.
Oh, yeah. Oh, he did.
Okay, so this
Sure.
Brian Conet fragment, I'm not sure if they pronounce it that way, but I know AIS is A as in Dore, so I can get that part of it right anyway. This is sometimes called the Adriatic Plate. Other people call it something else, and there's, of course, Africa. So those are your main elements. Let's look just a smidge at this one. The Beriscan orogeny again occurred about 300 million years ago. In North America, we call that the Allegheny orogeny. That's the result of Laurentia, North America, colliding with Africa and Europe to form the continent Pangaea. Okay, so if you're familiar with the Allegheny orogeny, if you've heard about that, Europeans give it a different name. But basically the same orogeny. Though in much of Europe, they usually give a little bit older age than that. So it's possible that the continents scissored together maybe a little bit earlier in Europe than what we have here.
A close word would be Berisca.
Yes, the Beriscan orogeny. So there's synonymous. Okay. So let's look at how these plates started to collide and what happened. According to our friends here in their book, they say that the very first part of the orogeny was this portion of the Adriatic plate subducting under, or being thrust under the main part of the Adriatic plate. So let's call it like this. We've got the Adriatic plate with a fragment of it going down like that. And then these oceanic rocks of the southern Penninic Ocean started to subduct. So that's the southern Penninic. That was followed. This is another little continental fragment that they talk about in the book. They call it the Cervinia terrane, but it's not mentioned as far as I could tell anywhere else. But then you have this Brian Conet fragment that then begins to subduct, so we'll call this Brian Conet. That's followed by subduction of the northern oceanic tract, so let's call that the northern Penninic, until finally the European plate starts to subduct underneath that. So basically I have a series of stacked sheets, all subducting pretty much to the south. And that's sort of what it looks like, a little block diagram. Note that north is out this way, so this is continental Europe up that way. So here's the European basement. Again, that is the stuff that's, I don't know if he's got it up here or not, that is mainly metamorphosed with granites, etc., coming in the Beriscan orogeny, the collision of the main continents to form Pangaea. On top of that, we have all sorts of sediments, and those get thrust out mainly to the north. The blue are the oceanic tract portions that are subducting underneath the brown. The brown is the Adriatic plate here. So they're all stacked off in that direction. Now these red things are domes of the external massifs. They are domes where you're seeing the basement poke up through these sediments. They've either been warped up or in some cases extension revealing them. So you will probably see several of those domes or massifs on your trip. There are internal massifs as well, such as this, fragments that have gone down into the subduction zone and were brought back up. Okay, so if they're internal to the oceanic tracts, they're internal massifs. If they're out here amongst the green sediments that are on the European continent, they're just portions of the basement that have been poked up. So Mont Blanc, for instance, is one of these. Mount Rosa is one of the internal massifs, etc. Okay, we'll come to this one. This is probably the most famous of all, the Dora, I'm not sure how to pronounce it. Meira, anybody know Italian? Dora Meira Massif. That one is absolutely cool. It's world famous. I'll show you why in just a second. So that put together produces this. The greens are the sediments on top of the basement on the European continent. These are the external massifs in red. So you have Mont Blanc. This is the Air. I don't know how to pronounce that. These lighter colored ones are the internal massifs. These are the ones that were subducted. So again, this is just a part of the basement that's been folded up where you can see it or thrust up. But these actually went down the subduction channel and then popped back up. The blue are all the oceanic rocks. And this is the Adriatic plate. Your trip goes something like this. I've tried to look at your map to see where you're going. You start here in Milan, right? Then you come over this way. You'll be over in these oceanic rocks. I don't know if you go near Mont Blanc. I think you cut up. You don't go to Zurich, but you go to Munich, right? So you cut across
no,
this.
we go to Zermatt.
Oh, Zermatt. Zermatt's down here somewhere. But you cut across this way according to the map, and then I think you do a loop like this. So you're going to go through a big chunk of that stuff. So that being the case, let's look a little more detail. So let me back up. This is more of a generalized map, okay, so you can see it a little better. The greens and this stuff are sediments on top of the European basement. These are the external massifs, basement of the European continent. Again, these will have experienced some degree of alpine metamorphism, but usually not a whole lot. Most of these, again, have the metamorphism and granitic rocks from the Variscan orogeny. It's about 300 million. These are the oceanic track rocks, and this is the Adriatic plate that's come up against them. Okay? Here's another little block diagram. These external massifs sometimes are just basically domes. Other cases you see that they've been fractioned and thrust up. North is out this way. This would be the oceanic track rocks. This is the Brian Conet terrain, and this is another oceanic belt. So this is some blob of crust that's surrounded by or sandwiched by oceanic rocks that were jammed together in the subduction zone. So the cross section, you get something like this. European crust, metamorphosed in the Variscan. These are sediments that are deposited on top of it. These have been thrust out this direction. They're called the Helvetic naps. The first one to go into the Adriatic plate was this blue. That is the southern Penitic oceanic tract. This is the Brian Conet terrain, that continental fragment that's sitting out in the middle of the ocean. Here's the other branch of the ocean that goes underneath the Brian Conet, and then the European plate goes underneath as well. Note that the Brian Conet terrain is this bulb-like thing. It says the massif lies like a huge bubble surrounded by oceanic rocks in the Earth's crust.
So this doesn't show the internal massifs, does it?
The internal massifs would be a fragment of something like this that went down and came up. This would be an external massif, maybe a fragment that's broken or domed up. So the external massifs are internal to this subduction channel stuff that went down. And I just put this in because I wanted to, because it's cool. Anybody recognize the green color? This is serpentinite. These are ultramafic rocks from the ocean that have been thrust up, and now they've been metamorphosed to low grades with serpentinite. So you have oceanic rocks from those terrains, oceanic belts that are actually quite interesting. And you will be going to the Matterhorn area, Zermatt. This is a fragment of the oceanic crust that is sitting now up in rather high elevations. Here's another one of those blobs of bubbles of the Brian Conet terrain that forms an internal massif, kind of popping back up out of the subduction system.
Is that also what the Dolomites are? Are they oceanic?
They are quite different in the sense, well, some of you guys probably know a whole lot more about the Dolomites, but those are, I believe, Triassic carbonates. They're sitting on a platform. Okay, and they were never subducted like this. All right, so now, this eventually gets us back to metamorphic petrology. This shows the metamorphic facies of the Alps. Now, one problem in this book I noticed, their abbreviations must be abbreviated from German, because they don't make a whole lot of sense. This is the subgreenschist facies, lower greenschist facies, upper greenschist facies, high pressure greenschist facies, epidote and fibrillite facies, blue schist, transitional blue schist, aclogite, and granulite. So I put this up here, even though the keys are wrong for us English speakers, to look at the map and say, well, gee, where do you see general regions of medium pressure, shall we say, orogenic type metamorphism, And where do we see regions of high pressure subduction zone metamorphism? So just look at the colors. I think in the beginning of the trip, again, you'll land here and head this way. What colors are you seeing?
High pressure.
High pressure eclogites, dark blue, transitional between blue schist and eclogite, and lighter blue, a lot of blue schist. It blew me away when I saw this because I work in the northern Appalachians, and you don't see very much evidence of high pressure metamorphism there at all. Most of it is just the classic medium pressure orogenic stuff. So I looked at this and I'm like, gosh, there's eclogites and blue schist everywhere in the Eastern Alps. Let's see, Mont Blanc is there. Zernoff, the Matterhorn is somewhere in this region. I'm not quite sure. John, you've been there a whole lot more. It's somewhere right about it.
It's just.
Yeah, it's not listed on this map, unfortunately. Okay. So look at this big belt of high pressure metamorphism. You probably can't see it from the back, but there's this little sliver from our perspective that's this brown color. That's ultra high pressure metamorphism, and I'll show you that in just a second. Now, as you swing around this way, what are we seeing? We're seeing a lot of, well, kind of green. So there's green schist facies going up to amphibolite facies here. You got this window. It's, again, I don't know how to pronounce it, Tauern window. I'll show you more later on. That's got green schist to epidote amphibolite facies to epidote. So all through this area, of course you get some blues here as well, and some purples over there. But through this central section, you have more of the collision, classic collision type metamorphism and medium pressure. Okay? And you'll be seeing all of these. So there's your path. And again, I've tried to piece these together. So Munich is somewhere up here. So you'll be coming across like this, cutting up through the high pressure stuff. Probably, well, here he says you go to Zurich is right there. So there's Zurich. So you'll be cutting through the green schist, perhaps up at the amphibolite. Do you go to Innsbruck? I'm not sure. But then you cut down somewhere through here. So you're going to be seeing a lot of classic metamorphic rocks. Let's look at the subduction zone metamorphic rocks first, the eclogite and blue schist facies. So here they are in blues and purples. Note that they show PT paths for us. A lot of them go very deep and then pop right back out. And if they spend a whole lot more time there, they probably swing out more this way and get hotter as they come down more of a classic PT path. But again, there's a lot of high pressure metamorphic rocks here. And that's where most of them are. This is what they look like. First off, this is actually something called pseudo-lawsonite. It's tough to get lawsonite to preserve. This shows the stability field of lawsonite. Here is your triple point for your luminosilicates. So below here is andalusite. From here on up is kyanite, and this is silmonite. So this area in gray is the lawsonite stability field, and notice it's less than 400 degrees. So you have lawsonite, you're not very cold, or you're not very hot at all, but boy, you can get pretty deep. It's up to 20 kilobars in this graph. But as it comes back down out, this line shows the stability field of lawsonite. As it comes back down this way, that lawsonite can get converted to other minerals. But it'll still preserve the shape of the lawsonite. So hence it's called pseudo-lawsonite, meaning it was original lawsonite. You can still see the crystal morphology, even though it's been replaced with other minerals. This rock, I'll pass this around later, because if I pass it around now, you go, ooh, I can't look at anything else but this, it's so beautiful. But these greenish minerals here are kind of rectangular shaped like this, and these are pseudo-lawsonites, just like these guys are. So if you see sort of orthorhombic, or shall we say rectangular type crystals, they very well could be lawsonite or pseudo-lawsonite. And again, there's its formula. It's a calcium aluminum silicate. How do you like that one? If you see a rock like this, get it. If you don't pick up this stuff, you don't get a degree. Okay? All right, what do we see here? The green. The green is green omphacite. Remember, ophiolite is basically augite clinopyroxene, but with some sodium and aluminum, enough that they don't call it augite anymore, they call it ophiolite. All this green is ophiolite. The blue. All the blue is glaucophane. Remember, that's the sodium-rich amphibole. Okay? These guys are all garnets. In fact, you can see these lasts of glaucophane sitting in the garnet. This brownish stuff is a carbonate. Anchorite is an iron-rich carbonate. So that's secondary. That's probably not related to this. Okay, that's an absolutely gorgeous rock. And the authors, this guy, I got it from his webpage, Dave Waters. He calls it blue schist eclogite facies transitional. So it's kind of sitting right between the boundary of those two facies. So that's pretty nice. You like that? Well, hang on. How about this one? So eclogite facies, again. By definition, eclogite facies has garnet and ophiolite. So here's a band of clearly eclogite. Notice this region, though, has garnet, it has some ophiolite, but it's got all the blue of glaucophane. Now, gee, that looks more like blue schist sitting next to eclogite. Oh, look at that composition. Desmond's been through this before.
I was just
So you might think, look at this rock, or when you look at this one, we've got clear eclogite right there, but these thin little bands of blue schist. Now, didn't I just tell you that blue schist facies is cooler than eclogite by perhaps a couple hundred degrees or so? So how could I have a band right here that's a couple hundred degrees of something a centimeter away? Probably not going to happen. Metamorphic petrologists love triangular diagrams, and there's an AFM diagram. I don't know if you saw those in petrology or not. See AFM diagrams? Okay. You recall that you can plot a bulk rock composition in the AF diagram, and at whatever pressure temperature condition, say if you're sitting right here, then the mineral assemblage will be defined by these tie lines. So if your rock composition is here, then the tie lines say, oh gee, I have ophiolite and I have garnet. So this rock will be a true blue eclogite. But if your rock is a little bit more magnesium rich, if you're out here, just crossing that tie line, then the assemblage will be glaucophane, garnet, ophiolite. In other words, just by a slight variation in iron-magnesium ratio, you can get a true eclogite sitting next to something that looks more blue schist. So this wasn't probably hotter than that. It's just that there's a slight band of composition difference. If you see it in the field, grab it.
So was this metamorphosed in an eclogite facies or a blue schist?
It's probably transitional right between the two, because they're the same pressure, temperature being this close. But this is just a little bit more iron rich than that. So you get the appearance of glaucophane there and not there. It's just a compositional difference. So if you see that in the field, don't freak out. Don't think, by golly, this should be hotter than that, because this looks blue schist versus eclogite. So composition plays a lot of, or a big role in the final assemblage. Okay, how do you like that one? What's this mineral? Garnet. What's the green? Ophiolite. What are these bluish needles? Glaucophane. There they are. Okay. I don't know if you go to this place or not. Western Alps in Italy. You probably go up through that area.
Close to it.
You'll probably be very close to that. So, I mean, every one of you should have a big chunk of this sitting on your windowsill somewhere for people to walk by and go, wow, that's so awesome. So grab some eclogites and blue schist. How do you like that one? This is probably a metamorphosed gabbro. These green guys are ophiolite, but when they're chromium-rich ophiolite, they have that absolutely gorgeous green color. So this is probably a gabbro. Again, it's been metamorphosed to eclogite facies. You can look at this later on. So if you see that, definitely grab that. Okay, it's absolutely beautiful rock. Metasediments go down into the subduction zone as well. And again, the classic Barrovian sequence that Barrow saw in Scotland, that you see in other orogenic belts, gives you a pressure temperature path right along it here. This is a mineral called carpholite, and here you see carpholite porphyroblasts, these guys, all throughout this schist. This shows the the pressure temperature stability field for this mineral. I must confess, I've never seen it. I've read about it, and when I found this guy's webpage, I said, oh yeah, there it is. So if you take sediment that would be a schist with silmonite, garnet, everything else under a typical orogenic setting, subduct that, then you get this mineral. Now, I don't know if Jeff will have a local geologist with you or not.
Or
I think some places he will. If he says, oh, this is a carpholite schist, then bing, 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 lights will go off. You'll know exactly what it is and make sure you grab it. Okay? So I want to show you these things so that if you do see them in the field, you'll have some sense of the pressure temperature. And he'll go, wow, you guys know a lot. So let's look at them in thin section. How do you like that one? Blue mineral, what is it? Glaucophane. Notice it's different degrees of blue. It's just a difference in iron magnesium ratio. See these little guys? What are they? Those are the baby garnets. There's little teeny garnets in this thing. And this clear mineral, I'll show you with the cross polarizers here. That is the phengite. Again, it'll look like muscovite, but compared to muscovite in a regular schist or in a perluminous granite, it has higher silica, magnesium. You don't care too much. But they call it phengite here. So cross polars, that's what you get. So again, here's the glaucophane. The garnets, of course, are isotropic. That is, they stay dark when you cross the polars. And here is the phengite right there. This also has a little bit of omphacite. See these greenish guys there and here? So there they are. So you get 4 different minerals there to see. How do you like that one? Garnet, glaucophane, a little bit of omphacite. Quite spectacular rocks. Okay. I mean, wouldn't you love to print that out and put that on your wall? There it is in the cross polars. The garnet's all fractured. It's got some inclusions in it, so it doesn't look as isotropic as the previous slide. But you can see a lot of the glaucophane still stays blue. Okay. Garnet, these are the omphacites. That's the phengitic mica. The omphacites tend to be green like that. So this is a true blue eclogite. There's really no, well, maybe there's a little bit of glaucophane right there. There it is under cross polars. These are from the Alps. Those other ones were samples that I made from stuff in Greece. I downloaded these from this Dave Waters webpage. So here you have an ophitic metagabbro, not very deformed. The large green chromium ophacites. Those are those beautiful big green ones I showed you in the previous slide, one of the previous slides, and the nice green ones here. Okay, so we have a lot of omphacites. These little guys in here are garnets. Okay. So that is a very good eclogite. Here's a blue schist. Yeah, Desmond.
Was that the gabbros, metagabbros, those coming from the ocean basement stuff?
Probably.
Probably coming.
They're probably an oceanic plate, that there were gabbros that have been broken and subducted, etc. You can easily see the glaucophane there in this blue schist metabasite. Basite is, I believe, a term that Brits use. Basically means a mafic rock. Here's a nice eclogite. Garnets, all these guys are the omphacites. Down here, there are some lawsonites that have been replaced. And lawsonite doesn't like to hang around. As it's coming down the retrograde path, it converts to other minerals quite easily. There it is in the cross nickels. There are your garnets. These are all your omphacites. And this is what's left of the pseudo-lawsonites down into there. Okay? So that's this area. Let's look at this just for a second. That little section of the Doramera, however that's pronounced, massif, that has ultra high pressure metamorphism. We've had high pressure already sitting here, but there's evidence of even higher pressure than that. I think one of you will give a talk on the microdiamonds of this complex. One of you have that assignment later on this semester? This on the syllabus, it says someone will be presenting something.
Ultra high pressure?
Yeah.
Yeah.
Okay. So just to give you a little sneak preview, I won't steal your thunder too much. This is the quartz coesite reaction. So at higher pressure, the quartz is converted to a silica polymorph called coesite. This is the phase diagram, if you've seen this before, to show you the silicates Here we have quartz, higher temperature you get tridymite, even higher temperature you get strobilite, remember those terms? But as you go higher pressure, you have coesite, and really, really high pressure, stishovite. So these ultra high pressure metamorphic rocks have evidence of coesite instead of quartz. And you can see the pressures that you're looking at. They're pretty high. And this is one of the rocks of the Doramira massif, eclogite facies, ultra high pressure. These are the garnets. Magnesium rich garnet, that'd be more of a pyrope end member. Phengite, phengite again is the muscovite-like thing here, probably there. Kyanite, I'm not sure where the kyanite is, it could be this. And quartz. Now wait a minute, didn't I just say this is ultra high pressure that have coesite? Why is it quartz? Well, if you're sitting here and then you drop down in pressure, the coesite reverts down to quartz again. But it does so with certain textures that are indicative that it was once coesite. Relics of coesite sometimes are preserved in the garnets. So the garnets may have inclusions of coesite, but all the stuff out here gets converted back to quartz. So the garnet acts as a, shall we say, a vesicle that traps the coesite and preserves it. So here is a schist, these are the garnets, and you might have little inclusions like this that could be coesite in the garnet. That's how it was first discovered. You gotta be a pretty good petrographer to look at little things in garnet like that and say, oh gee, that's not quartz, that's coesite. Well, this was first discovered in 1984, and as a result, this section of the Alps is very famous. These are the phengitic micas. Here we have garnet again. Some of it's being converted to talc. Some, not in this section, but other sections you find little inclusions that are still coesite. But this is quartz over here. And it says the quartz domains on the left show a columnar structure called palisade texture, which probably results of the inversion of coesite as the rock dropped in pressure and coesite was converted to quartz. But notice it has these elongated quartz grains like that. Okay. This is what palisade quartz looks like. This was an inclusion that was coesite. You have little remnants of coesite left, but a lot of it is quartz, and when it converts back to quartz, it has that kind of texture that's indicative of, hey, I was once coesite, now I've dropped down. Here's another one from this region in the Alps. It's a quartz inclusion with little fragments of coesite in it. But what happens when coesite, which is the high pressure mineral, converts to quartz, there's an increase in volume. And the garnet fractures. So there are radial fractures around these things that were once coesite. This is an ophiolite from Norway, but again, the radial fractures are there. So this guy who first saw this probably said, gee, what are all these fractures doing here? That would suggest there's been an increase in volume that made him say, gee, that's quartz, that could be coesite, boom, big discovery. The guy's famous. Okay. So those are the type of things that a petrographer would look for, and that gave indications that these rocks weren't just high pressure, they were ultra high pressure. There's one more mineral in here that says ultra high pressure. If you zoom in on these garnets, in that little triangle, you see this, little diamonds. This is a messy diagram over here because it's got all these other lines that indicate composition. But that's the coesite quartz reaction. This is the graphite diamond reaction. So above that, any of the graphite would get converted to diamond. This shows PT pass for rocks from the Alps. Notice they get up to 4 gigapascals, that's like 40 kilobars, 40 times on average 3.3. You're well over 100 kilometers depth when you're getting up into this region. Okay.
So this might be a weird question, but can you make any profit out of a rock like that?
Well, that's 40 microns.
So,
So if you gave your fiancée that diamond, she wouldn't even see it. If you could, it'd be pretty cool, wouldn't it? But they're really, really tiny. And again, one of you will discuss the micro diamonds. So these did indeed experience ultra high pressure metamorphism. And it wasn't until the 80s that people actually started seeing these things. Now, notice there's no coesite out here, there are no microdiamonds out there. They're only preserved where they're trapped in a container. Because as they come down that path of lower pressure, they get converted to lower pressure assemblies on a retrograde path. So you can have good eyes to recognize ultra high pressure metamorphism. All right, let's move to the regular shall we say, continent collision type rocks. These are where you have the Barovian metamorphism, that's the medium pressure here. Reference, Barron here, Zerk I think is up there somewhere. And you've got this big window over there. What faces are you seeing? Lower green schist, Upton Fiblite. Okay, that's normal. You see that in ocean or in mountains all around the world. The Alps are kind of cool because you got all that high pressure stuff that you don't see in the Appalachians, you don't see much in the U.S. unless you go more to California. So this shows, let's say, this window. Why is that window there? Well, you get the rock sliding off and this being popped up, so it shows you the basement complex. So what's in this window? Briskin basement. That's just the old European continental crust. Certainly doesn't look very mafic. In fact, it's not. Granitic gneiss. So this stuff would have been metamorphosed during that Briskin collision 300 million years ago or so. A lot of these are granitic gneisses. For instance, here we have a statue of St. Barbara somewhere up in the high pass. That's kind of cool. You go up in the mountains and I'll see all sorts of stuff. But I put it in here because you can see the felsic gneisses. So what kind of textures would you see? Okay, we're not seeing the high pressure path now. We're seeing the more standard medium pressure stuff. So what do we got? Epidote banded greenstone, metabasaltic rock from that window. Okay, same for the previous figures. Containing albite, that's the clear stuff here. Chlorite, this darker green is the chlorite. Epidote is this stuff right here. Minor actinolite. Remember what actinolite is?
The needle?
Actinolite is it's a type of amphibole. It's a lower grade amphibole. And that would be this stuff right here. Titanite, which is sphene, I don't know, it's probably this stuff in through here, and opaque oxides. Okay, so what do we got? Epidote and fiblite facies. Medium pressure path. Garnet, chloride. From that, somewhere, I don't know what this is from. Okay, so we get garnet zone stuff of upper green schist, lower epidote facies. Okay? See this all around the world. That's pretty normal. This is a really cool one. We have starolite. Have you ever seen starolite in petrology or mineralogy?
Yeah.
Okay, starolite's a beautiful rock. One of the best rocks in the world for starolite is in Maine. I have pieces to show you if you'd like. This is the chlorite. This bluish green mineral is called chloritoid. Now you've probably not heard of chloritoid before. Think, why would a rock have chloritoid? And it seems like it's coming out of nowhere. Don't panic on this, but I put it in for nerds like Desmond.
Yep.
Again, it's an AFM diagram. We're just going to look at a couple of them. Okay, here's an AFM diagram. If your bulk composition is right within that triangle, then at 520 degrees, you're going to have the minerals starlite, chloritoid, chloride. Exactly what was in that previous slide. Most metasediments aren't that aluminum rich. Most of them plot down here. Hence, most don't have chloritoid. So if you're out in the field with some geologist in the Alps and he says, oh, this is a chloritoid bearing schist, lights flash off, bing, bing, bing. Oh, that's going to be fairly aluminum rich to be sitting way up here to get chloritoid. At higher grades, as we go from 520 up to say 560, notice the chloritoid disappears, and then we get starlite, garnet chlorite, even at that same pressure temperature condition. So chloritoid tells you something about the bulk composition and temperature range. But anyway, and this is again stuff you'll see all around the world. We have garnets, we have kyanite, we have biotite. So a graphitic kyanite garnet schist. See all these black little stringers through here? That's the graphite now. Okay, carbon was in the original metasediment, and it gets metamorphosed to graphite. These are probably iron titanium oxides, probably ilmenite. With all those little things are graphite. Okay, so this is pretty normal too. Again, classic orogenic medium pressure metamorphism. So, just to overview that part, most of the subduction zone stuff is here. Collision of continent type stuff here and through this window. With some really cool ultra high pressure stuff. Now that's not to say that there wasn't ultra high pressure stuff over here too, but it may not be preserved. It's preserved there because you have them trapped in the garnets that show you what you want to see. Okay, so all that is up here. Now notice the brown colors, those are from the Adriatic plate, and there's a pretty distinct boundary that cuts right through here. That boundary is basically called the peri-Adriatic line. Now it's named different things for different segments, because one guy down here doesn't talk to one guy over there. But this book calls it the Adriatic line. And these are different cross sections across the Alps. Let's just look at this one for a second. Here we have the nappes that are thrust out over the European plate. Those are mainly cover rocks that were on the European plate that got jammed and thrust out. These are the rocks that are the oceanic plate that went down. You have the brine connate terrain that went down and popped up. Some of those are ultra high pressure. This forms what some people call a pop-up structure, a flower structure, a dorsal zone. These rocks are popping up this way and to the south down that way. Notice this stuff is now covering and coming up over this unit. So this is this line that we're seeing expressed up here, and basically now it's a dextral strike slip fault pretty much. The Alps, from my perspective, are really weird in the sense that they have very little granitic material in this origin. I'm from New Hampshire, it's a granite state. Everywhere you walk, oh, granite, granite, granite. Everywhere. Partly because there's so many sediments that were jammed in there that they melted and produced granites all over the place. But there are very few granites in the Alps. And they're mainly associated with this peri-Adriatic line. So here they are. As an igneous petrologist, I find that pathetic. What do we got? 8 stinking plutons. Okay? Their ages, this one way over here to the east is 19 million years. All these other ones are between 30 and 34 million years old. That's basically the age of this strike slip fault. Okay? And they're coming up along that fault and then splaying out into the rocks alongside it. How does that happen? Well, if you read this book, they say, well, it's kind of controversial. There are various ideas. One possibility, it's one I favor, as this plate subducts, it may break off eventually, slab break off. As it sinks away, then you have upwelling of the asthenosphere filling its void, placing hot mantle rocks against lower crustal rocks, partially melting those lower crustal rocks. And as those magmas are formed, they say, well, what's the easiest way to the surface? Well, right here along this fault. Okay, so many plutons will come up and migrate along faults to where they reach their buoyancy level and balloon out. So they'll do something. Whoops. Let me show you this one. The most famous of these is the Adamello batholith sitting right here in northern Italy. Here is a map of that pluton. All these are different faces of the pluton. Notice it's a composite batholith where you have a pulse that comes out, another one comes in, another one comes in, and another one comes in. It's just sheet after sheet, or pulse after pulse of coming in, ballooning out more to the south. So the magmas are coming up the fault. And how does that happen? Well, take this one for instance. If you have faults like this with a bend in it, every time that fault moves, it gives space so that the magma can come up. If this happens multiple times over a long period, then the interior can be filled with a granite. Or you may have a magmatic blister that come along the fault and bulge out like that. So you get this sort of thing happening time after time after time. What kind of rocks are these? This one's pretty cool. Gabbro pegmatite. It's probably big amphiboles, very coarse grained. This one's pretty cool too. That's D. Hand sample of hornblende quartz diorite. Remember the term quartz diorite? Remember your triangle for granite, classification quartz, plagioclase, alkali feldspar. This plots down to the plagioclase corner, and these are all amphiboles. A lot of these plutons are granodiorite. Amphibole, probably biotite. I don't know if you'll see these in the field or not, but they're late in the orogenic system. There certainly aren't very many of them, again, which is surprising to me, who's used to orogenic belts that are loaded with granites, like the Sierra Nevada batholith or the Appalachians, northern Appalachians. But that's what they are. So again, you'll come something like this, up through the high pressure stuff, across the medium pressure stuff, coming back down somewhere through here and around. So you may not actually see them. Why? Because there just aren't that many, which is again very surprising to me. Okay? Desmond.
What's the timing on the collisions of these? As far as is there a shift from
from the west to the east as it hits one place and then rotates. Was a rotation involved in this?
There is
it pretty-
rotation. From what I've read, it appears as though the rotation is counterclockwise now, and that's why this thing is shifting this direction, but that's late, and the granites are very late. Okay? So you have a sense of what you're gonna see? I'm gonna gather some cool rocks for us and put them in collection. When you see blue minerals, you know what they are? Yeah. Okay, you have a sense for high pressure and maybe even ultra high pressure. And of course, you won't see evidence of ultra high pressure with your eyes. You need microscopes to see that. All right, so there's an overview of the metamorphic and the few igneous rocks there are in the Alps. All those external massifs are basement rocks that were formed 300 million years ago that may have experienced some degree of metamorphism during this collision. As far as granites go, not much. Okay, now if you want, come look at this blue schist, eclogite with stringers of blue schist because of compositional difference. Here's another blue schist eclogite. This one has beautiful green omphocytes, and this one has the pseudolaucinite. Okay, so feel free to come look at those if you'd like.